Most modern microcontrollers, they have a PWM output that you can control the duty cycle, like you can control the duty cycle, like how it goes on and off, by programming it. So that's how the PWM is usually created. But just we wanted to see like the concept of sinusoidal PWM using comparator. That's very easy and like very basically sweet to understand, like how using DC voltages, like we only have two levels of voltage, VDC and negative VDC, actually three levels and zero. Using only like three DC voltage levels, we create a signal that basically create an AC current for us, right, using PWM. And so if you use PWM, your harmonics are going to be smaller. You wouldn't have pulsating torque, as I mentioned earlier. Like your motor is going to run smoother because it wouldn't sense these discrete signals. Like these signals are much smaller than the time response of the motor. It's similar. I always compare this to like watching a movie. Like when you watch movie, you're basically seeing 24 discrete pictures in 1 second, but our eyes cannot detect it because our eyes are not as fast, right? They see like a continuous motion. It's the same thing here. Like you have pulses, but these pulses are so small, or like happen so fast and so frequently that the motor wouldn't sense them. So we wouldn't have that pulsating problem. We wouldn't have overheating. One thing that we would have using PWM is that we would have a lot of switching losses. You remember that we calculated switching losses for DC-DC converters. So here, like, we also have switching losses. So that's something that we have to consider. Also using inverter, we would have harmonics. We still need to have an LC filter to filter out the harmonics based on the standard, like which harmonic to what level we have to use the filter to do so. Like, why do we use switches, or like why do we get gate signals to turn the switches on and off? Because in like basically what I'm asking, like why don't we just like use microcontroller to turn the switches on and off, like instead of providing gate signals? Because the output current of a microcontroller's output current is usually very low compared to what we need to turn like a high voltage switch on or off. So that's why we use MOSFETs, we use switches, we use IGBTs to provide the small current from the microcontroller here to turn this one on. Like this is going to be much higher than this one, right? So that's why we use microcontrollers. Another thing I want to mention is that what you see here, this one, like if even if it's like this is for unipolar, and if I do bipolar, it would be something like this. It'd be something like this. So you see, like the width starts increasing, like it mimics like a sinusoidal, right? Like sinusoidal, it's a small gets to a peak and then goes down, right? It's the same, but for the pulse width. So the width of this one gets bigger and then eventually gets smaller again, gets smaller again, gets smaller again. And for the so for the you remember for bipolar we only have like one comparator, right? So like then because we want to turn the other switches on and off, like we want to have like a negative voltage, then it basically the same thing happens for the zero voltage. So like it would basically, this pulse, look at this one, then gets a little bit bigger, gets a little bit bigger, gets bigger, and then continues. So this is like how you mimic having a sinusoidal. So both of these, I'm sorry, I wrote this one VDC, that's wrong. This is the gating voltage. This is applied to the switch, not to, this is not VDC. Okay, I'm sorry I did that, but like for this, for voltage, right? But it generates like once you have the switches on and off, your output voltage actually looks like this. That was actually correct. This is VDC, negative VDC. This one is the gating signal I'm applying to the bipolar, right? So then if it would basically create something like this, yeah, just like, because you remember we don't have the zero negative, so it would just like be something like, right? And then the negative part gets bigger. If I want to do bipolar, this is VDC, this is negative VDC. This is the gating switch that we apply to S1 and S2, and the complement of that is applied to S3 and S4. Yes, S3 and S4. And this is like what we end up having at the output. I'm not doing a good job in drawing this, but if you look at your lecture notes from Dr. Jeff, he has like all this in the lecture notes, so you can actually see the waveforms here. But you can see that here we mainly have positive voltage, here like we mainly have negative voltage. You see like the positive portion is very small and the negative portion gets bigger and bigger. This basically mimics a sinusoidal waveform, okay? Both of these are called two-level inverters. Okay, we only have positive VDC and negative VDC, right? Here, like we have zero as well, like, but I'm saying like at the actual voltage level that we have positive VDC and negative VDC, right? We also have multi-level inverters, which we're not going to discuss in this course, but I want you guys to know because it's very commonly used in the industry. If you remember, when we discussed rectifiers, we did 6 poles, 12 poles, 18 poles, right? Like by adding multiple levels, right? So it's similar concept happening in the multi-level inverter, right? And what you end up with is like having voltages that just doesn't look two level, like it would have multiple levels. So I can just like draw this here, for example. And then like maybe something like this.